Have you ever wondered how spacecraft slow down after hurtling through space at incredible speeds? It's an intriguing question, isn't it? This process, known as spacecraft deceleration, is a critical aspect of space exploration. Without it, successful completion of space missions would be nearly impossible. It's not as simple as hitting the brakes on your car. It's a complex process that involves physics, engineering, and a fair bit of cosmic finesse. So, let's delve into the fascinating world of spacecraft deceleration. To understand how spacecraft slow down, you first need to grasp the basic principles of physics involved. Let's dive into it, shall we? Picture this. You have a ball in your hand. You throw it, and it moves. That's momentum, the product of the mass of an object and its velocity. In the context of a spacecraft, it's the same principle. The spacecraft, once propelled into space, continues to move due to the momentum it gained from the launch. Now, we come to force. Newton's first law of motion tells us that an object in motion will stay in motion unless acted upon by an external force. In space, there are few forces to counteract the momentum of a spacecraft. This is why they can keep moving for years without any additional propulsion. But when we want to slow them down, we need to apply an opposing force. So, how do we create this opposing force? One way is through the spacecraft's engines. By firing the engines in the opposite direction to the spacecraft's motion, we can slow it down. But this method requires a lot of fuel, which adds weight and cost to the mission. Here's where the clever bit comes in. We can also use the atmosphere of a planet or moon to slow down a spacecraft. This is known as atmospheric drag. As the spacecraft enters the atmosphere, it collides with air molecules. These collisions create a force that opposes the spacecraft's motion, gradually slowing it down. This technique, also known as aerobraking, is a highly efficient way to decelerate a spacecraft without using any fuel. However, it's not as simple as it sounds. The process of atmospheric deceleration requires precise calculations and timing to ensure the spacecraft doesn't burn up in the atmosphere or bounce back into space. Now that we understand the basic science, it's time to discover how it's actually applied in real space missions. In real space missions, slowing down a spacecraft is a complex process that requires careful planning and precise execution. Let's delve into the details of this fascinating process. When a spacecraft needs to slow down, it carries out what's known as a retrograde burn. This involves the spacecraft changing its orientation and firing its engines in the direction of its travel. The thrust from the engines acts against the spacecraft's motion, effectively reducing its speed. It's akin to hitting the brakes in a car, but in the vacuum of space, where friction is non-existent, slowing down is a bit more complex. Now, imagine the spacecraft is approaching a planet or a moon with an atmosphere. Here's where atmospheric entry comes into play. The spacecraft is moving at such high speeds that the friction with the atmosphere generates intense heat. To protect the spacecraft and its precious cargo, heat shields are used. These shields are made of materials that can withstand and dissipate the intense heat generated during re-entry. They bear the brunt of the heat, allowing the spacecraft to slow down gradually and safely. These methods, while sounding simple in theory, require precision and high levels of engineering innovation. The calculations involved in determining the timing and duration of the retrograde burns, or the design and material choice for the heat shields, are all critical components of successful space missions. So, through a combination of physics and engineering, spacecraft can safely decelerate and complete their missions. Spacecraft deceleration might seem like a daunting topic, but it's actually a fascinating blend of science and engineering. It's a journey we've taken together today, from the fundamental principles of physics to the intricate dance of forces in the vast emptiness of space. We've seen how the invisible hand of atmospheric drag plays an essential role, slowing down spacecrafts as they re-enter the Earth's atmosphere. We've delved into the world of retrograde burns, a crucial technique used by engineers to change a spacecraft's speed and direction. Heat shields, too, have had their moment in the spotlight. These unsung heroes protect spacecraft from the extreme heat generated during re-entry, ensuring the safety of the craft and its precious cargo. We've unraveled the complex fabric of how spacecrafts decelerate, making a topic that once seemed daunting, accessible, and intriguing. Next time you watch a space mission, you'll know exactly how that spacecraft is slowing down. And who knows, maybe one day you'll be the one planning a spacecraft's deceleration.